Okay, I'm back. We'll continue. We may not have time to touch the well-ordering principle. I think I may just concentrate on the consideration today. We'll see, okay? Depend on time, okay? So let me give you two more examples on how we can use the recurrence for counting. This one is a very familiar example for you. Actually, we know C and K denote a number of different ways to choose K objects from n distinct objects. Another notation for C and K is this one, n to k. All of us know the closure formula for this one is n factorial divided by k factorial and n minus k factorial. For small k, of course, we can compute this number by using this formula. It's not difficult. But for large n, it's not easy because multiplication for large number is more difficult. So perhaps we can use another way to compute this number. Another way is to find the recurrence relation for this one. Because the recurrence relation, as we have seen earlier, many relation is just something adds with something plus something. So it's quite easy to compute, right? Even by hand. So perhaps we can discover the recurrence relation for this one as well. Then maybe we will be able to use this to compute this one more effectively or more quickly or easily, okay? So let's see, what recurrence relation can we be obtained for this one? How can we obtain recurrence relation for this one? All right, so let's take a look. So we have n objects. So now we want to find a number of different ways to choose k objects. So our target is choose k objects. So let's focus on the particular element. So this particular element, x. In order to choose k objects, there are two ways. With respect to this particular element, there are two different ways. Either we choose x, or we don't choose x. Only two different ways when we choose k object. Either choose this particular x or do not choose it. If we choose this particular element, the remaining problem is to choose k minus 1 objects from the rest. So here n minus 1 objects. So if we choose this one, so number of different ways, once we choose this x, will be Cn minus 1, k minus 1. So we choose x already. Now we choose k minus 1 element from this n minus 1 element. Okay. Another way is we don't choose x. If we don't choose x, we have to choose all k objects from the rest. Okay. So that will be Cn k. So there are only two different ways in order to choose k element. Either choose this x or do not choose this x. And they're totally different. There are no overcounting because here every element will involve x. Here every element, every subset, k subset. Here every k subset involve x. Here no k subset involving this x. So therefore they're totally disjoint. Total number of different ways is just summation of these two. So that gives us the calculation. Okay, so that's the recurrence relation for this one. Now, of course, we need to give the initial conditions. I'll leave it to you to fill the initial condition. All right, so initial condition, what's initial condition? So I'll leave it to you to figure it out. What's initial condition for this one? How many equations do we need for initial condition? Okay. It's really worth to find out initial condition for this one. Look, here it's kind of two-dimensional. It involves two things, two parameters instead of single parameter. So the whole thing looks like a two-dimensional table. Okay. the whole thing look like two-dimensional, not like a Fibonacci number. It's on the line. So here are the two-dimensional table. All right. So I leave it to you to find out initial conditions. All right. So that's the recurrence relation we obtain. So instead of computing this number by using this formula, we can also compute this number by using this recurrence relation. Now here is in connection with algorithm. So one way is just to compute it, use recursive calls to compute this one directly. So all of you know recursive calls, right? You have studied programming language. So can you recursive call to compute this one directly? All right, some of you may want to try it. If you try it, you will see it is almost impossible to compute, to obtain this value in reasonable amount of time or even in unreasonable amount of time. When n is large, is just maybe over 100 or something, or 50 will be good enough. Slightly large n. It only works for very small value of n. Only for very, very small value of n, you will be able to obtain the value of nk by using recurrence calls based on this recurrence relation. Only for very small value of n, maybe in the range of 20, 30 at most, I think. If n is a little bit bigger, say 50 or 100, and if you use this recursive calls to compute this one, you will never get the answer. Okay. So the reason is when we compute this one using this recurrence relation, Cn, let's see, maybe let's not use x. Okay. You maybe use an r. Okay. According to this one, for same value of r, may occur many times. So there are a lot of repetition of computing same term if we use direct recursive call to compute this one. Six, the problem of causing the trouble. Actually, running time of this one is exponential. The running time of this one is exponential in terms of n, in terms of the k. I am sorry, in terms of n, not k. Okay. In terms of n, it's exponential. So it's very, very slow. If the running time is 2 to the power n, for small n, it's okay. If n is 20, it's okay. But n is 50 or 100, running time, it's dead, right? It's impossible. It will be roughly 10 to 30. So that's the reason we cannot effectively compute this number by using recursive calls. However, this recurrence relation is still very, very useful because we can use this relation to compute this one in a clever way. Instead of recursive calls, we can use so-called dynamic programming. We can use dynamic programming to compute this one. To compute this one. Using this recurrence relation, not using recursive call directly, but use this recurrence relation. But rather, use the idea of dynamic programming, use bottom-up approach, we'll be able to compute this one very, very quickly. So that will be subject of algorithm course. Okay. But here the main point is recurrence relation really come into play very often when we design algorithm, of course, when we do counting. So here, both in counting and in designing algorithm, recurrence relation play a very important role. Here we see in counting, to count this one, we can obtain this recurrence relation. And once we obtain this recurrence relation, we'll be able to use it combined with the dynamic programming technique to compute it efficiently. So it must be, so in this case, it needs to be combined with dynamic programming idea. Otherwise, we will not able to compute it efficiently. All right. Okay. So here's one example in connection to counting and dynamic programming. So next, I will give you one more example. It's has something similar to the previous example, but it's a little bit more involved. Okay, here's the problem. We still choose k objects from n objects. So we have n objects, we want to choose k objects. Now the requirement is these k objects whose sum equal a given number. So give you k integers. Okay, so here the object will be positive integers. I have k integers. So maybe 15, 25, maybe 63, 45, maybe 28. Okay, so here I give you 12 numbers. I allow you to choose, say, 5 numbers, maybe 5 numbers. So k equals 5. So here n equals 12. So here n equals 12. Okay. So here I want to find 5 numbers from these 12 numbers whose sum may equal W equal maybe 256. Now question is, I want to not only find such a set, but want to determine a number of different ways. How many different ways I can find k numbers whose sum equal 250? Okay, for this one, I think it's very difficult. I have no idea whether it exists or not. One way, of course, to exhaustive search, so n to power of k. So this is very bad. We can do it in this way, n to power of k. But this will not give us number of different ways mathematically. Algorithmically, we can determine number of different ways by doing exhaustive search. So we find a number of different ways. But mathematically, how can I find a formula to determine the number of different ways? So that's what we want. Okay, we want to determine number of different ways. So find the k number from n number whose sum equal W. So this was very difficult. Okay, let's work on a very small example to see how it works. Okay, so here maybe just only 6 numbers, n equals 6. K equals 3 maybe. Now this set can be multi-set. Some number same, it does not matter, it can be same, okay? So if we're looking for different patterns, so that's okay, okay? So let's say we want to something maybe equal 10. So we want to find the 3 numbers whose sum equal 10. So what's the number of different ways? So for example, in this particular case, it can be, say, 1, 4, 5. That would be one solution. Another one is 1, 2, 7. Okay. So perhaps only two answers here. Okay. If I add one number, so maybe 6. So then 2 to 6 is also a solution. Okay. But otherwise, perhaps only 2 different ways. Okay. So without this one, This one. Okay. So here multisets, it's okay, also okay. So some number maybe same number, but not. So some number can be used here twice. That two can be used twice. All right. So what we want to do is find the recurrence relation for this one, number of different ways. All right. So let's use in the note. I think I use G. Let's see the ordering. Actually, in the notes I did not give details. So let me see. Number. Okay, use GKWS. Okay, so suppose we use GKWS to denote the number of different K subsets inside S whose sum equals W. So this problem, okay? So we want to find the recurrence relation for this one. So once we have the recurrence relation, actually, that will give us a better way to determine this number. Instead of using this one algorithmically, we can use, in the worst case, we may need to exhaustively search with this much time to find out this number. But once we have the recurrence relation, we can do much quicker than this one. All right. So we can use very similar idea as what we have done for N2K. So what we do, we fix an element. So suppose that's a set one need to work with. So that's a set S. Okay. That's set S. We consider a particular element here. So maybe anyone does not matter. So this is a particular X. So using very similar idea as previous example, a K subset. A K subset is solution if its sum equal W. Okay, a K subset. So maybe a solution. Okay, so consider particular X. If X is contained in a solution, then we have one situation. Another way is X is not contained in a solution. So that's very, very similar to previous example. Two ways. Consider particular X. Either X belongs to a solution or does not belong to a solution. Okay. So we have two cases. X either belongs to a solution either belong to a solution or belong to no solution. Only two cases for this particular X. Okay. Now let's see what happens under this situation. So recall the previous example. It's very, very similar to the previous one. But there are one subtlety. So if X belongs to solution, then what happens? So then the problem we need to solve, we have choose one element already. If it belongs to a solution, now K is reduced by 1. Now summation. This summation. Originally value needs to be W. Now X is chosen. So for the rest, K minus 1 integers, whose sum should equal to W minus X. Originally, its value, summation should be W. Now X is chosen. So for the remaining K minus 1 elements, its sum needs to be W minus X. Okay. Now, where does these Where do these k minus 1 elements come from? Originally, k elements come from S. Now these k elements, so in this particular case, integers come from S minus X. If k is true, X is chosen. So that's what we have. All right. Now here one thing, one subtlety I need to point out. So for this one, originally I said 250, right? So W equals 250. Suppose I have some more integers. There are integer called 400. So this 400 will never be this particular X. I don't need to consider this one as X because the value more than W. So that means when we consider this, the value of X as X should be at most W. Then we consider this situation. All right. If it's more than W, then we do not need to consider this X. So that's one thing different. X is less than at most W. All right. Otherwise, does not belong to any solution. So that means I still choose k elements, k integers, and whose sum still equal W, but it's from the rest of the set. So we do not choose X. So there are these two situations. Okay. So either this case or this case. Total number of solution will be summation of these. So it turns out this one is so actually anything more than W, you can slow away out. But another way is slow these number away as well, okay, because they never contribute to the solution. You can do it in this way. So what happens is for every so that's the current relation we obtain. Okay. So this recurrent relation will be foundation for dynamic programming algorithms to solve the subset sum problem and the net set problem, which you will be discussing algorithm course. Actually, these two problems are really very difficult. The subset sum problem and related problem called the net set. These are so-called NP complete problems. It's a very difficult problem, but with this recurrent relation as a foundation, we'll be able to solve them relatively quickly. Okay. So instead of exhaustive search, we don't need to do exhaustive search, but rather can use this one combined with, again, dynamic programming. So we can solve this problem relatively quickly. In practice, for many for many practical cases of success sum, actually we'll be able to solve it very quickly, even in polynomial time. Okay, but this again, it's not scope of this course. Okay. All right, I think we'll give you two more examples. Give you two more examples in connection with algorithms. Both have something related to algorithm. One is shortest path. So here are the load map of street map. Okay. Suppose you want to get one place to another. So suppose you are currently here, maybe. Okay. So X. You want to get to from X to Y. Maybe Y is here. Maybe this Y is not best. I don't know. Y is here. All right. So you want to get from X to Y as quickly as possible. So this then relates to finding a shortest path from X to Y. Okay. Now, in terms of time, because the load condition, so we know that maybe from here travel to here takes maybe here 2 minutes. So here maybe 5 minutes because load condition different. Here 3, maybe here 2, here 4, maybe here 1, 5, 6, 1. Suppose you have these ideas, all right? So the okay, so we have a number for each section of the street between two intersections. And I want to find the quickest time or the quickest way route from X to Y. How can I find it? So here maybe 4, okay? So without giving the number initially you solution perhaps you just say, just taking this one, okay? When you look at this one. Okay. But actually maybe this one is better. This one is better. So how can we find such a shortened route from one point to another? One way is to find the recurrence relation. All right. So let's see. Maybe I add one more. Add 2 more. Yeah, 5. So one way to do it, maybe let's see, without the time, maybe then you maybe T. I still use D maybe distance. Okay. Okay, so let's use dxy to denote shortest distance from X to Y. Of course, here distance may not mean physical distance, so it may mean a time here. Okay. But in general, we just call the distance. Distance or even cost, whatever it is. We distance to denote the quantity you are interested in. So here, in practice, maybe time, not the physical distance. Okay. So, but normally we call it distance. So we want to find the shortest distance from X to Y. So one way to do it is you find the recurrence relation for computing distance. So let's look at the problem from X point of view. So in order for X to get from X to Y, what X can do, X has 3 different ways. Either take this route, takes this route, or takes this route initially, okay? Only 3 different ways. So then get into intersection. Then for each intersection, there are different ways. So I will not write a general one, but for this particular case, what we can see is, so let's denote C3 maybe as X1, X2, X3. Because in general, we need the graph theory, the term from graph theory, which we haven't taught yet. It will be taught towards the end. Maybe later November, we'll teach graph theory, okay? So we need some notation. So here I will just use this example. So in order for X to get from X to Y, what X will do is either take this one or this one or this one. Only 3 possibilities. So for each, we can express the distance from X to Y in terms of distance from X1 to Y, X2 to Y, X3 to Y. Okay. So for in this particular case, what do we have? So it can either take this one. If we take this one, its distance will be, let's denote maybe as this one. Okay, so for each load, load is actually use W to denote this weight. Okay, so from X to X1, then distance from X1 to Y. So if it takes this one, or takes this one, then it will be X2. Or this one. All right. Now our answer will be minimum of these three. So will be minimum of these three. Okay. So we get a recurrence relation of dxy in terms of dx1y, dx2y, dx3y. So of course, in graph theory, we have term for these things called the neighbor of x. So I can write as neighbor, but for this particular case, since I haven't introduced this notation, I will just write in this way. Otherwise, we have terms called neighbor of x. We can express it rigorously. So here, this will just illustrate the idea how we can represent dxy in terms of smaller dxiy. So this gives us the recurrence relation. Again, we can use this one to obtain the algorithm to compute the shortest path. The classical algorithm, Dijkstra algorithm, is related to this one. I cannot say exactly same from this one, but actually very, very closely related to this one. Okay. So for me, it's actually from this one, but for it's yeah, one can say it's really based on this one. But the form it appears in textbook is different from this one. But actually it's based on this one. All right. Okay, so finally give you another example related to algorithms. All right. So here I will do it in 2 dimensions. So on this is a plane. Okay, on the plane there are endpoints. So give me endpoints on the plane. I want to find a pair point that is closest. So pair points whose distance is minimized among our pairs. So just P1, these endpoints. So I want you to find the Pi, Pj. The distance is minimized. So that's called the closest pair. Okay. So for this particular example, perhaps a human eye maybe can do things in parallel. You will see that perhaps either this pair or this pair you immediately exclude a lot of possibilities. But in order to compute it for general input by computer, it's not that easy. One way, of course, is to try all possibilities. So there are n squared possibilities. We can do exhaustive search. All right. Again, so n squared possibilities. For every pair, we compute distance and find one that minimizes. So, but time it takes will be proportional to n squared. However, we can obtain a recurrence relation that enable us to reduce time from n squared to n log n. Actually, it's very significant, n squared to n log n. Because if n is 1 million, log n is only about 6. Also, if base 2 is 20, okay, log n is 20. Base 10, of course, is 6. Okay, so reduction is very significant from n squared to n log n. So one algorithm is again based on a recurrence relation. So that's what I want to discuss, recurrence relation. So what we do is again, in order to solve the original problem, we reduce the problem to smaller problem of same nature. So in order to do this, to find the closure pair among endpoints, now I will reduce the problem to a smaller problem. So that's where the recurrence comes from. Okay. So what we do is divide the points into 2 parts. So here left, here right. So number of points will be roughly half of n for both sides. All right. Now, in order to solve the original problem will compute the distance. So this denotes this one with minimum 1. So delta equals minimum 1. So use this notation. Okay. Affects the right upward. So that's the distance we want to find for closest pair. Okay. So what we can do is for both sets, we have delta L, delta R. So we find the closest pair for this part, closest pair for this part. We get these 2 numbers, LR, delta L and delta R. All right. So what we want to do is to compute the original one. So this set, we want to compute this notation of see, maybe okay. Delta S. So endpoints. So here is delta S. So that's what we want to do. Okay. So of course, what we see is this one. Of course, is at most delta L, delta R. The solution for the whole set of points is at most subminimum of solution for this side and this side, of course. Okay. Now, in order to get a recurrence relation, it is possible that once we have this division, some points close to this line may be smaller than this one or this one. So that's why this here less than equal, not same. So for these points, we need to compute it. So there may be points like this one. So there may be, so this one is happen to be on this side, it's okay, but it may be the case. We have 1 point here and 1 point here. So maybe 1 point here. So for these pairs, we still need to see whether their distance for these pairs. So whether their distance is smaller than this minimum 1. If it is, so then we should take this distance as our solution. All right. So what happens is we need to work on a particular region here. So it's consider strip whose width is 2 delta, where delta is minimum of left side and the right side delta. So delta L, delta R. So we consider this strip. Okay. So within this strip, so call this region, let's see, it's a vertical strip, maybe call it B. Okay. All right. So now we have 3 values. So we have a number from left strip, sorry, left region, and a number from the right region, and number from this strip. All right, so we have 3 of them. We have delta L, delta R, also have delta B from this vertical strip. Now the current relation is original one. Let's see, shift it. So that gives us the following recurrence relation to compute the distance of closest pair for endpoints. This delta S is saying it will be minimum of delta here and left side and the right side. So these 3 parts. All right. Now, the point is that actually for this particular part, it's easier to find the closest pair. For these 2 parts, it's still difficult. We will keep on using the same idea to do it. But for points within these 2 delta strips, the time to find this one is quicker. So we'll be able to find this one quickly. And eventually, these 3 together can be combined to find a closest pair in time n log n instead of n squared. Okay. So you see that really the recurrence relation come in very, very often when we deal with mathematical problems or algorithmic problems. So actually, this one is not trivial example, but it's to illustrate the idea it comes. And it's a base, the foundation for solving this problem quickly actually is based on this recurrence relation. And it's also give you an idea how to analyze the problem in order to obtain recurrence relations, which is very, very important for computer science students. Because eventually, if you want to design an algorithm using divided count method or using dynamic programming, the first thing you need to do is to find the recurrence relation. So this example illustrates the idea to discover the recurrence relation. So eventually we get this one, which is not easy at all. Okay. All right. I think I will stop today. And Wednesday, I think I will discuss the well-ordering principle, a tool for prove things. And mathematical induction will be delayed to next week instead of this Wednesday. Okay. All right. Okay. So see you. Thank you. Thanks for today. Lunchtime.